Hello students, Professor Nugent here. This is the last video in our introduction to panel data. We're going to think about panel data with more than 2 time periods. Panel data methods extend naturally to more than 2 time periods. Before we think about writing down the model, let's write down our assumptions. First, we need to be able to assume a balanced panel. That is, for the same t time periods, or for each of the time periods, we have a complete observation of the n cross-sectional units. Alright, so we're saying that the n cross-sectional units show up for all the time periods. None of the cross-sectional units are missing in any of the time periods. Next, we need to be able to assume that the covariance between explanatory variable xj for individual I in time period t, between that attribute and the error term uis, individual I time period s, that the covariance between these two things is 0 for all t, s, j, and we're missing an I. This is a very strong assumption, and indeed it's referred to as strong exogeneity or strictly exogenous. And we're going to assume that this holds after we difference out the fixed effect. We will be able to relax this a little bit when we get to more advanced panel data methods, but for now we're going to assume that this holds. Now keep in mind that this strict exogeneity assumption does rule out cases where future explanatory variables react to current changes in idiosyncratic errors. So this rules out the ability to use a lagged dependent variable. More on this briefly. We will also see that omitting time varying variables that should be in the regression equation, also measurement error, violate this assumption. So these are our 2 assumptions that we require for panel data with more than 2 time periods. Let's write down the equation. We have, the assumptions are met, we can write down the general fixed effects model. The general fixed effects model is for I equals 1 through n and t equals 1 through t. So we have t times time periods and n observational units. We can write y it is equal to delta 1 plus delta 2 d2t all the way through delta t dtt. So observe that we include a year dummy for each year in the data set minus 1 plus beta 1 x1 it through beta k xk it plus ai plus uit. we're going to first difference this equation. And first differencing this equation gives us delta y it is equal to alpha 1 plus alpha 3 d3t through alpha t dtt, and then we have our beta 1 delta x1 it through beta k delta x kit plus delta uit. So we've differenced out that pesky fixed effect. We have also rewritten this equation with an intercept, alpha 1, and t minus 2 time period dummies. And we've done this because otherwise the first difference equation using this set of dummies results in an equation without an intercept. And we know that that results in some difficulties with interpretation of the coefficient of determination, the r squared, and for inference. We also have to make the assumption that delta u, it are serially uncorrelated over time, so that our t and f statistics are valid. This is usually too strong of an assumption, and clustering can help us obtain fully robust standard errors in test statistics. More on this in this data tutorial.